Hello, my name is Brian Cooper. Just to remind you of who I am, I am a biology and chemistry high school teacher in the school district of Philadelphia. And after 13 long months, I am finally back in the building. So this is my innovative lesson. It's titled The Marble Roller Coasters. It's one of my favorite lessons that I do. So let's get to it. So what are the big questions of this lesson? So the big questions are, what does math have to do with thrilling roller coaster rides? How high does a coaster need to be to successfully navigate through a loop and on the end of the track? How is the speed of the coaster related to the height of the coaster's starting position? So here's a summary of the lesson. Students build their own small-scale model roller coasters using pipe insulation and marbles, and then analyze them using physics principles learned in the associated lesson. They examine conversions between kinetic and potential energy and frictional effects to design roller coasters that are completely driven by gravity. A class competition using different marble types to represent different passenger loads determines the most innovative and successful roller coasters. Engineering connection. So during the design of model roller coasters, students encounter many of the same issues that real-world roller coaster engineers address. In order to build working roller coasters, students must recognize the constraints placed in their designs and the design of real roller coasters by the fundamental laws of physics. Students learn that their ability to understand and work within these constraints is paramount to the success of their roller coasters. So here are the learning objectives. After this activity, students should be able to explain why it is important for engineers to understand how roller coasters work, explain in physics terms how their model roller coasters work, discuss the effects of gravity and friction in the context of the roller coaster designs, use the principle of conservation of energy to explain the design and layout of roller coasters, identify points in a roller coaster track at which a car has a maximum kinetic and potential energy, identify points in the roller coaster track where a car experiences more or less than 1 g-force, and identify points in a roller coaster track where a car accelerates and decelerates. So the education standards are based on the next generation science standards. They are to develop a model to describe that when the arrangement of objects interacting at a distance changes, different amounts of potential energy are stored in the system. Construct, use, and present arguments to support the claim that when the kinetic energy of an object changes, energy is transformed to or from the object. And develop a model to generate data for iterative testing and modification of a proposed object, tool, or process such as an optimal design can be achieved. So things that are going to be needed for this lesson, you're going to need pipe insulation, about 1/2 inch, and you're going to be cutting them in half lengthwise. Usually one side of the tube comes perforated, making it easy to use scissors or a utility knife to cut through the perforation, and the other side of the tube to form 2 halves, essentially making 2 long channels perfectly shaped to hold marbles. Thus, one cut tube provides the track material for 2 groups. Glass marble, wooden marble, steel marble, paper or plastic cup, a roll of masking tape, a set of markers, crayons, or pencils, blank sheet of paper, a stopwatch, the roller coaster specifications worksheet, 1 per student or 1 per group, and the suggested scoring rubric, which is going to be 1 per group. What is the prerequisite knowledge that students are going to need to know? Students need basic prior knowledge about forces, particularly gravity and friction, as well as some familiarity with kinetic and potential energy. They should also know Newton's second law of motion and understand the basic concepts of motion, such as position, velocity, and acceleration. So the introduction motivation. You're going to start your lesson out by saying, during today's activity, you're going to design your own model roller coasters using foam tubes and marbles. I'd like for you to start by drawing your roller coaster on paper before building it. Along with your drawing, give your roller coaster a fun and descriptive name and make a sign for it. At this point, show students photographs of some real roller coasters to help them imagine the possibilities for their own coasters. You can see some examples of some of the best current roller coasters in the country at ultimaterollercoasters.com/coasters/pictures. So then you're going to want to identify the needs and constraints to your students. So when engineers design objects and structures, such as the appliances in your home and other products you use, bridges and roadways, skyscrapers, and other structures like amusement park rides, or even bicycles and chairlifts at ski resorts, they work within what they call constraints. Constraints are project requirements and/or limitations. Engineers must take into consideration these constraints in order to come up with successful design solutions. So then you're going to ask your students, in the case of designing roller coasters, what might be some constraints that engineers would have to consider? At this point, you're going to let students think about this and make some suggestions. Eventually, you're going to respond yes. They might have some practical limitations, such as available or preferred building materials, a construction budget and time frame, safety measures for users, ongoing maintenance requirements, and/or anticipated weather conditions. You're going to try to prompt and guide your students to these answers. Then you're going to say the amusement park client may also give requirements for the type of movement they want for the ride, such as upside down loops, corkscrews, specific degree turns, length of jocks or maximum speed, or safety assurances for users, meaning safe for people taller than 4 feet high. Another basic constraint that always applies is consideration of the natural physical laws that exist in our world, such as the limits of gravity and the effects of slope, speed, and friction. This is an example of how engineers' understanding of the fundamental laws of physics is very important to the success of a project. Coming up with a design solution that takes all these factors into consideration and works reliably, safely, and intended is what engineers do. Then you're going to ask your students, when designing your roller coaster, what are the physics concepts that you have learned that will be helpful and very important to apply? You're going to listen to your students' ideas, correct and amend as necessary, and expect them to suggest ideas from the content they learned in the associated lesson about gravitational potential energy, kinetic energy, gravity, and friction. Then you're going to respond, that's right, all true roller coasters are entirely driven by the force of gravity. The excitement of a ride comes from the ongoing conversion between potential and kinetic energy, which we know from the law of conservation of energy. Friction is important to slowing down roller coaster cars, and acceleration plays a role in the experience provided by roller coaster cars as they move along the track. Then you're going to ask, and how do these concepts translate to your challenge to design a roller coaster that provides a thrilling experience that is safe for riders? You're going to listen to your students' answers and expect to hear them bring up the following points, which they must understand in order to build and analyze their model roller coasters. This includes the top of the first hill must be the highest point on the roller coaster. Cars move fastest at the bottom of hills and slowest at the top of the hills. Friction converts useful energy into heat and must be minimized. G-forces greater than 1 occur at the bottom of hills. G-forces less than 1 occur at the top of hills. To avoid falling, cars must have a certain velocity at the tops of loops. So then you're going to say, that's right, these are constraints you must take seriously. The first hill must be the highest point or the roller coaster won't work. If a car is moving fast enough at the top of the loop, it will fall off the track. Pay attention to the friction between the car and the track, making it as small as you can so the cars move fast enough to make it through the entire track. Let's get started. So before the procedure that you're going to do before the activity is you're going to gather the materials and make copies of the worksheet and scoring rubric. Then you're going to cut each tube in half lengthwise, so each group receives 1 length of tube that is channel shaped to serve as the roller coaster track for the marble cars. Use scissors or a utility knife to cut through perforated side of the tube to form 2 halves. Give each group 1 of these halves. My suggestion, as someone who has done this before, if you're going to use scissors, make sure you use those kitchen shear scissors, because cutting them with safety scissors will take a very long time. Then you also want to review the steps of the engineering design process, and you're going to follow these steps following these steps while building the students build their roller coasters will help them learn exactly how roller coasters engineers solve the problems. The engineering design process involves ask, research, imagine, plan, create, test, and improve. So now it's time for the procedure with the students. You're going to divide the class into engineering groups of 3 or 4 students each. Hand out the scoring rubrics for the class competition, which you can see right here on the right side. The list of creativity points provides students with guidance as the coaster features, such as height, turns, loops, and corkscrews. These are desired in the design, and the list of performance points provides a way to judge the safety of the coasters. You want to tell the students that in our roller coaster models, the glass marbles simulate a normal car, the wooden marble represents an empty car, and a steel marble represents a full car. Your team will earn points for each type of marble passenger load that successfully completes your track and lands safely in the cup. A class competition will determine the most innovative and successful roller coasters. Then you're going to have groups start designing their roller coasters, brainstorming and sharing ideas, and agreeing on a design. Have students draw their roller coasters on paper, name them, and make signs. Allow up to 30 minutes for this. Then you're going to look over their drawings to ensure that their proposed designs are physically possible. If not, point out those aspects of the roller coaster design that they may want to rethink. Give them time to iterate their designs. Give each group a foam tube track, masking tape, and a cup, and let them build their roller coasters using classroom materials. Expect students to be able to build their first design in 10 minutes or less. Use the cup to catch the marble at the track ends. Here is an example of a design. As you can see, they kind of utilize, what are these called? Ring stands. Yeah, the ring stands as helpful parts of the roller coaster. There are different parts of my classroom that I let students use. They are free to be as creative as they want. So then you're going to give students marbles so they are able to test their roller coasters and make any necessary changes. This is the most time-consuming step, and students may need to take 45 minutes to redesign their tracks. So this would be really good if you have block periods, but if not, it may take more than one day, and if that's the case, you might want to ask to have a separate room for those. So hand out a stopwatch to each group and give them time to complete the worksheet in which they determine certain specifications of their roller coaster. So then we do the competition. You're going to start the class competition by telling the students, similar to what you did today, engineers create small-scale models to help them test and analyze their structural designs. For example, the engineers who designed the Golden Gate Bridge in San Francisco were pioneering new suspension bridge design theory. They verified their complex calculations, all done without computers in the 1930s, of the forces it would need to withstand by performing tests on a steel tower model at 1 to 56 scale. That's 56 times smaller than one of the actual bridge towers. The test confirmed that the tower calculations of the anticipated forces, including wind, earthquake deflections, were sound, and the bridge still stands today more than 75 years later. Have each group present its roller coaster model to the class. Use a scoring rubric to evaluate the roller coaster model designs. Then discuss the results as a class. So then how are you going to assess your students? Well, there is activity embedded assessment, which is an assessment done within the activity. And there are 3 ways you can do or options that you can choose from. The applied physics embedded assessment is to check that each group understands how and why its roller coaster works. If a roller coaster is not working, ask students what they think the problem is. See if they can identify physics constraints and explain problems such as, it's not high enough, or the marbles rub too much. In physics terms such as, it doesn't have enough potential energy because it's not high enough. Or, the friction between the marble and the track is too great. The embedded assessment of determining velocity is to have students measure the length of their roller coaster, which can measure the distance of the length of the tubing and the time it takes for the marble to complete the track. Ask students to calculate the velocity of the marble in meters per second, as well as in feet per second. Then you can have them graph. During testing, graph the relationship between the height of the first hill, the independent variable, and the average velocity of the marble, the dependent variable. Describe the relationship, for example, as the height increases, the velocity increases. And then you can have them do a worksheet, have each student or group complete the roller coaster specifications worksheet, which asks them to identify some critical points of the roller coaster, as well as other specifications such as the height and the number of loops and turns. Review students' answers to gauge their comprehension of the concept. The roller coaster worksheet can be seen right here on the right-hand side. And then if you want, you can have them do presentations. Have each group present its roller coaster model to the class. Use the suggested scoring rubric to evaluate the roller coasters for the class competition. Discuss the results as a class. You want to ask your students, which roller coasters were the most exciting? Which were the safest? Which one for creativity? Which one for performance and safety? Which model best met the overall challenge for both thrilling design and safety? What were the trade-offs? So a point you can make is that engineers call this optimization, balancing competing project requirements. What did you learn from testing your model? If you were to redesign your roller coaster, what improvements would you make and why? What would happen if you engineers ignored the fundamental laws of physics in their designs? How important is it to you that engineers test their designs for things like appliances, cars, bridges, stairways, roller coasters, before they are built and people use them? And what engineering design steps and techniques do we use today? The answer you're looking for is brainstorming, modeling, simulation, testing, analyzing, redesigning, and optimization. These are all things you want to guide students to. All right, so that was my innovative lesson plan. I hope you all enjoyed it. Thank you for watching.